Hello, this is Matthew, and welcome to part 3 in this video series on multi-value databases and pick-like environments, where today we'll be talking about programming in these environments. As we can see from this 1985 copy of the Pick System User's Reference Manual on archive.org, the way that you program in the Pick system is using this QMBasic language. And it says right here, the QMBasic language is an extended version of Dartmouth Basic, specifically designed for database management processing on the Pick system. So they started with Dartmouth Basic, developed in 1963 at Dartmouth College, and added features to it that have to do with being able to use the database files on the Pick system and some other enhancements that weren't yet in the original Basic all the way back there in the early 60s. But I do want to take a moment just to talk about the fact I'm recording this video on November 17th, 2024, and just a few days ago, on November 14th, Professor Thomas Kurtz passed away. He, along with his colleague John Kemeny at Dartmouth, was actually the inventor of the basic programming language. So really a pioneer in the field. And when you think about how pervasive BASIC has been, not just as an educational language, as it was originally targeted for in a time-sharing system for computer science students in the early days of time-sharing, and actually having computer access available to all of the students rather than just extremely constrained batch processing resources. That alone was pretty revolutionary in terms of how you can then go about teaching computer science and programming, actually having a computer available. Imagine that. But I think back to when I was a kid, and really my very first exposure to even the concept of source code and what computer programming was back when I could get those books, 101 basic games for the PC, 101 basic games for the Apple II. And many of you who watch this channel, of course, are going to be old enough to remember these things. Some of you may not, but you could actually get printed books, and they literally had, in the case of 101 basic games, the source code just printed in the book for 101 different computer games. Most of them not particularly engaging, we must admit. But you'd sit there and you'd type the game into your computer from the book. And you would, of course, make mistakes typing it, so you'd have to figure out what went wrong. And that's how I learned what programming even was. And that was, of course, all in BASIC. And you had to sort of figure out how to how to read the program. So if something did go wrong, you could try and figure out what it was, what you might have typed wrong, and go in and fix it. And then, not just those kind of silly little things like the 101 basic computer games, but if you think about how many businesses ran on and probably still have running, line of business applications or helper programs or automation programs that were built in things like Visual Basic, right? VB6 is sort of the last real version of Visual Basic. I think Microsoft kind of killed the spirit of Visual Basic when they tried to bring it in as VB.net, and it's just a totally different thing now. But good old VB6, right? That's how consulting shops built programs to run on Windows in businesses. That's how a lot of in-house developers built little programs to help run the business. So it really did, turn into this pervasive thing in our field. And Professor Kurtz was, of course, behind that programming language development. So big loss for the computer science community. He did get to live a nice long life, living to, 96 years old. So pretty impressive there. So back to our modern implementation of a pick-like system in OpenQM, and we're actually using the ScarletDME community fork of the last GPL release of OpenQM. We talked about that in the last video. But this has QMBasic. So really all of these multi-value systems are using the basic language as the foundation of the built-in programming language. Again, dating back to how the original Pick system did it, and most of these grew out of some desire of compatibility with both Pick and then all of the other environments that replicated Pick. But they all have their own little twist on their own customizations to the language, their own functions that are built in. So in the case of OpenQM, we are working with QMBasic. So before we dive back into it, I do want to point out, where does this come from? Because there is complete reference information for OpenQM for that GPL release 2.6.6, which was the last GPL release. It's what ScarletDME is based on. And probably the easiest way to get it, there's a great website here, rushflat.co.New Zealand, NZ. And the person behind Rushflat, I think this is probably his consulting company, has actually written a quite comprehensive book, getting started in OpenQM Part 1, Part 2. And this is we can see here a couple hundred pages of introductory material teaching you about OpenQM. And this was written somewhat after the 2.6 release was out. So there are a couple of things that are just in the later versions of the commercial releases that don't quite apply to our open source release. But by and large, it's 99% relevant. And I believe there's actually a section here where he does talk about the fact that there's the open source release, and he lists the couple of functions that he uses later in the books that aren't quite the same. I'm not quite sure where, but you'll get the idea. So this talks about creating the databases, the query language, a lot of the things that we looked at in the last video. And then part 2 of this book series gets back more into programming in OpenQM. It mainly focuses on using a terminal emulator called AccuTerm, which is a commercial product that is actually also now owned by Rocket Systems. And it has tools to actually create a graphical user interface application. It connects just using Telnet to the OpenQM server. And then I think it uses almost like a Kermit. It might actually use the Kermit protocol, or basically, though, a serial terminal protocol to communicate with programs that you write inside OpenQM, and then it draws the GUI components on the client side. But AccuTerm, it's a closed source proprietary product. It's only for Windows, so it's not really something that I'm interested in. We're just going to stick with building text terminal applications using the native capabilities of the PIC-like systems like OpenQM and ScarletDME. But that's not to say that this isn't a valuable book, because it really does teach you the basics of, no pun intended, how to use the QMBasic language. And just even reading through some of the parts about how you would program using this little GUI toolkit with AccuTerm, you do learn a lot about how to read records, how to open files, all of those kinds of things. So really still an excellent getting started guide, sort of tutorial guide to teach you a lot about the system and the environment. But this is also where you can download archived copies of the help files for OpenQM 2.6-6. And then if you extract those, you get, it's all a bunch of HTML files. If you just open the file in your web browser locally, some of the JavaScript that makes the being able to toggle open the contents and navigate through the contents doesn't quite work right. So I just spun up a VM running a web server and dropped them in that web server and hosted it through an actual web server, and everything works correctly. If you just open the file, you'll still be able to navigate through it using the list of contents on these top level pages. It just won't expand so that you can quickly jump down that way. So it works just fine, but it's a little more convenient to serve it up in a web browser. I'd love to actually host a little web browser in the Docker container that I made for running ScarletDME or OpenQM. But these documentation files, as far as I know, were never released under the GPL license or another freely distributable license like the actual code was. So I believe this is still just, as it says right here, right? Copyright material by Ladybridge Systems. So I don't think they particularly care that people are passing around the documentation for that version, but just in terms of keeping the source repository that has the GPL license on it clean, I am just going to keep the documentation out. So you would need to go and download it from some of the places online where you can get to it. But it's there, it's easily accessible, and it is a complete reference to the entire system. Every command that you can run from the TCL prompt is there. The documentation for the whole query processing language is there. And of course, the basic environment, the QMBasic documentation is here with all of the statements that the language supports, as well as some additional subroutines that are part of the system that you can call. So really good information to have at your fingertips. And if you are just getting into these systems, it's a good idea to read through the intro, read about the command environment, read about the file system. Right, if you're going to do any serious work in a system, you really want to have the foundational understanding of what's going on. So you should be aware of most of the things that are talked about in these introductory chapters of the documentation. In addition to the help files, you can download this documentation archive. This has a couple of PDF files. One is the reference PDF file. So that is the entire help content. So it's all of this exact same material. It's just in a more of a book style PDF. So if you want to load that on your e-reader or print out certain pages to have for quick reference, this is all available in PDF form as well. It also has a quick reference guide. So that'll have, like I said, just quick reference to key bindings for things like the screen editor. It'll have all of the formats for the different dictionary entries, and I think probably the vocabulary file entries, stuff like that. So good quick reference if you don't want the whole documentation printed out. And it has its own tutorial. So it has the OpenQM tutorial by the actual OpenQM developers. So that might be something good for you to run through as well if you just want to get started. You install the Docker container, you have a Docker system up and running that has ScarletDME in it. You'd be able to run through the OpenQM tutorial just to get your grounding in creating some database files and doing some queries. So that's where all of this documentation comes from. And that is really the only reference we're going to need today. So let's switch over to the terminal. I have my Docker container still running from the last videos, ScarletDME with all of my ports still mapped through to it. So we'll go ahead and SSH in. I would always recommend using SSH to connect right now. The Telnet, going in through Telnet, uses XINetD, and it doesn't set up the sudo terminal the same way the SSH session does. That's my theory as to why this happens. But we won't be able to drop to the shell or use full screen shell tools like VI if we go in via Telnet. So I'll just keep connecting via SSH and everything works perfectly. Before I do that, let me just remind myself what my terminal size is here, because we're going to tell our ScarletDME session what the terminal size is so that full screen stuff works correctly. I haven't written my auto terminal size detection program yet. I should probably really get around to that, but maybe after we learn about programming, I'll have the knowledge I need to do that. So 112 by 28. Okay, let's connect. That was on port 4222, QM user at localhost. And this will give us our TCL prompt. So we're connected into the system. So the first thing we'll do is just that terminal command. So 112 columns by, I think it was 28 lines. And now full screen tools will work correctly. One concept that we need to touch on briefly before we can start programming that we didn't talk about in the last video is a little bit more on the files in the system. So if I list my files and restrict it to local files for this account, I guess the first thing we should talk about is what is an account. So an account is what you would probably call a database in another database server like Postgres or MySQL or Microsoft SQL Server. You make databases. One server can have multiple databases in it. So it's the same concept here with ScarletDME. And I'm probably going to use the words ScarletDME and OpenQM interchangeably because the system itself really still calls itself OpenQM. It's based on that OpenQM code. So in an OpenQM system, you can have multiple accounts. An account is not a user login. So just like in Postgres, you can have multiple users who are allowed to connect to a database and work in that database. You might have some users that have read-only permissions on the database. You might have others that have read-write permissions. In a ScarletDME account here, it's the same idea. You can have multiple users on the underlying Linux system that have access to a particular account. So you might have the sales account for your sales application, and all of your salespeople would have logins that have access to the sales account. So don't get confused by the word account and think that it's an individual user. Think of it as a database that multiple users can share. Now, if we drop to the shell, which we can do just with the TCL command sh, you can see that because we connected as the QM user to SSH, we are sitting here at a shell prompt as the QM user, and we are in the QM data QM user directory. So in this case, the QM user directory is the directory for this account, which happens to be called QM user. Not to be intentionally confusing, but in this case, the account name happens to match the name of the user that I'm logged in as, but there's no relationship between the Linux user QM user and the OpenQM account called QM user, other than the fact that I have the QM user Linux user set up to, by default, be in the QM user account directory. Hopefully that's not confusing. I just want to clarify all of that. Now, if we look at the QM user account directory here, we actually see all of the contents of this account, of this database. We see the planets file that we created. We can see that there is this thing called voc, the vocabulary file. We can see the saved lists. So even though it's called save lists in the database in OpenQM, we can see that the data path name is actually $SV lists. So you can assign different names to data files in the underlying operating system. Some of these have dictionaries as well, right? So the planets dictionary is planets.dic. The planets data path is planets. So anyway, you can see the correspondence here. If I actually look in this planets directory, which is my planets data path for the planets file, we just have this -0 and -1 record or file. So if I look at that, it's just this big binary type file. So of course, in the database, like I said, these things are stored by key value paired. They're stored in such a way such that you can look up the data by key quickly. So this is just the internal file format that OpenQM uses to store data. But we know we added the Jupiter record to this file, planet number 5. And sure enough, you can see here, yeah, okay, so the data is in here, Jupiter. And then this hex code FE, this is 254. So that's the file mark, the field mark character. And if we go into one of our multi-valued fields, we see that, Pioneer 10 is separated from Pioneer 11 with the hex code FD, which is 253, which is the value mark character. So this is, getting a bit distracted here, but yeah, so these are just the actual files on disk where the data is stored in that internal format. But the reason I wanted to point that out is if we come back to the TCL prompt here by exiting it out of the shell, when I create a file, it normally creates it in that format. This is called the dynamic hash file format, which is the native format for OpenQM to store data in. But we have another option. We can say create file and call it plain text, and we can make that a directory file. So dictionary files are always going to be those dynamic hashed files. But by saying directory, we created the data part of the file as a directory file. So if I list my local files again, we can see here's plain text and it's directory type versus this planets file, which is DH, and the vocabulary file, which is DH. Now, these other sort of default system files are also directory files. But the important thing here is the plain text directory file. It still gets a data path name. So on disk, we're still going to see a directory called plain text. But if I start adding records to this file, so I can just do that with the line editor, for example. I can edit the plain text file, and let's edit a record, just call it, ID1. And just say this is my test file, blah, blah, blah. If I file that, let's go back to the shell. So as we expect, I'll do -F so we can see that these are all actually directories. As we expect, we have that plain text directory. But unlike planets, where it was just that -1 or -0 -1 file, we just have a file here. Now it's 1 because the record I edited was 1. And if I look at that file, that's the contents of record 1 of the plain text file, to use the OpenQM language vocabulary. Similarly, I can just create an arbitrary file in this directory. Let's create a file, an entry or a record for the key dogs. So dogs, you might have Samoyeds, you might have Cane, is that how you spell it? Cane Corsos, you might have Pit Bulls, you might have Golden Retrievers. So now I have a record with a key of 1, and I have a record with a key of dogs. If I come back into OpenQM, if I copy to terminal, file plaintext record 1, we of course still see that. If I copy plaintext record dogs, you'll see that each line in the file becomes an attribute in the way that the system treats these directory files. And if I say delete file plaintext, it'll wipe it out. If I go to the shell, plaintext is no longer here. So it basically manages it like it manages its normal data files, but instead of storing them in that efficient hashed dynamic database format, it just stores every key. It stores the value for every key in that file as a file on disk in the directory. Now, the reason this is important is because this is by far the easiest way to manage your source code file. So if we come back into the TCL prompt here, if I create a file, and I'm going to switch to the documentation really quickly here, you notice it automatically created that dictionary. If I'm making a file to hold source code, I don't really need a dictionary for that. So if you look at the create file command here, which is right here, you can actually say optionally there's this portion, which can be data or dictionary. So I can create data files on their own and dictionary files on their own. So I'm just going to create a data file with my file name, and then type is where we said directory. So let's create file, data, and the traditional name for the file that holds your basic program source code is BP. So we'll call it BP. And this is going to be a directory file. Now, this way, as I create my basic programs, I can just edit them on disk in that BP directory that just got created using my favorite editor, VI, whatever you like, rather than using the editors that are built into ScarletDME, OpenQM, which aren't quite as featureful as, say, Vim. So if I list my local files now, we can see that we have a BP file for our basic programs. It's a directory file. And on disk, its data path is BP, and we don't have a dictionary for this. So we're not going to be able to run those access queries against it using column names, attribute names, stuff like that. But that's okay, because source code for programs doesn't really have a fixed set of fields that are known attributes. So let's see what an actual program looks like. We will go back to the shell. So there's that. We can go into that new BP directory, which is empty right now. If you had, I don't think I have Git installed. No, if you had Git, you could just git init this directory, and then you could keep all of your basic source code under revision control. The .git directory isn't going to confuse or mess up OpenQM, so you can keep them under version control that way, which is nice. But I'll just create a program called Hello World. So the basic programs have to start with either program or I think subroutine or function. In this case, this is a standalone program that you can run, and it is called Hello World. And there's a command called display. You can also say CRT. This is how you print things to the terminal. So I'll just say CRT Hello World from QMBasic. And then you put an end statement down at the end of your program. So if we go back here, you need to compile the programs. So this is actually a compiler, a basic compiler. It'll compile it to, I think, some form of P code that the OpenQM environment is then able to run. So a little more efficient than having an interpreted version of BASIC, where every time it's having to interpret the subroutine code and all of that. You'll actually get a compiled version of your code here. So the way you compile it is with the basic command. So I'll say basic hello world. By default, it will look in the BP file for your basic programs. So that's another good reason to use the default or sort of the typical file called BP, is because then you're not always having to type the file name of where your basic program record is. So basic hello world will compile it. It created an output file called bp.out, which is where the compiled code goes. So that's not there by default, but it created it for you automatically, and it's just another directory file called bp.out without a dictionary. So now that it's compiled, I can run hello world. And sure enough, as you'd expect, we have hello world from QMBasic. So you can directly invoke shell commands by just putting them after sh. So I'm going to say shvi bp/hello world. And that'll drop us right into vi. And then when we quit vi, we're right back here in the TCL prompt. So now you can just hit the up arrow and hit enter to edit this program again. So let's just make this slightly more complicated, but not that much more complicated. Let's ask, what is your name? And then we can say input and the variable that I want to read the user's input to. So I'm going to call it username. And then we'll say, hello. We use the colon to concatenate strings and values. So I'll say, hello, username. Nice to meet you. Okay, let's compile this program again. So basic hello world. That compiles it, and then run hello world will run it. Okay, it's kind of working, but probably not quite how we thought it would. We still say hello world. We ask, what is your name? And then I put a question mark on the end of that. But now I'm on a new line. There's a question mark. What I type is abutted right up next to that question mark. So it's a little bit, it doesn't look quite as nice as I was hoping. But the program does work. It says, hello, Matthew, nice to meet you. It's substituted in what I typed there. So let's edit our program again. As we saw, the CRT command is automatically appending a line ending after whatever we display. So we can prevent it by doing that by ending it with the colon. So essentially, I want to display that line concatenated with nothing versus concatenated with the default new line. We can also set, and usually you do this for the scope of your whole program here, you can set the prompt to just an empty string. And that will prevent the input from always putting a prompt, the question mark, in front of the user input area. And I think to make this look nice, we'll just put an extra space there. So now I expect the cursor to end up right after what is your name, question mark, space. And that should probably look a little bit nicer. So we'll compile that. We'll run that. And yep, sure enough, what is your name, question mark, space. And if I type in here, I'm able to do that. And hello, Matthew. Nice to meet you. So that's the basics. Again, no pun intended. And I promise I will now stop saying no pun intended every time I use the word basic when I'm talking about the programming language basic, when I'm not actually referring to the programming language basic. Okay. So what else can we do here? We have a set of, let's say, input, enter, and let's actually just say CRT, press enter to continue. There is a function which will generate some terminal control codes, mainly used for positioning the cursor, but you can also do a couple of other things. And that function is the @sign function, and it can take 1 or 2 parameters. So it also takes a couple special parameters. So if I say CRT, because I want to display the output of this function on the terminal, @-1, this will actually clear the screen. I can also give it coordinates. So I want to print to the terminal the output of the command or the output of the function @. And let's say I want to go to coordinates 5, 5. Now this function, right, this is actually going to return the terminal control codes, right? So like the VT100 escape sequences. So that's why we use CRT, because we actually want to send those characters out to the terminal so that it actually takes effect. And remember, it will put still a new line after this if I don't put the colon there. So you'd actually, if I just did this and then I said CRT hello, in fact, we can try that. This will print out on line 6 instead of line 5, because we sent the control sequence to the terminal to set us at coordinates 5, 5, but then I'm going to get a new line and I'm going to be at the beginning of line 6. So we can compile that. We can run that. It does the thing. You press enter to continue. Yep, and we're back at the beginning of line 6, not, right, I can't highlight it, but right above the O is where position 5, 5 would have been. So we can fix that. We know how to suppress the new line. That would be one way to do it. We can also, of course, just print that sequence and then print the word that we want to print. And we could further combine this into just one statement by saying, okay, write to the terminal the clear line character sequence, the positioning sequence, and then the string that we want to output. So let's try that. Sure enough, now that works exactly as we intended it. Well, what else can we do here? So we know how all this works, so let's delete our name stuff. Using magic numbers like -1 is usually discouraged. So there is a system-wide available include file, and we can include files with the include directive. And there's a file called syscom.h. So we tend to use the convention of .h for include files that have things like symbols or other definitions, similar in C where we'd call them header files with .h. But we have this syscom.h, and it will define, among a bunch of other things, that'll give us a symbol called, I think it's ITCS for clear screen. Let's see if that compiles. It does not. We're going to look in the documentation here. Oh, include record syscom.h not found. Oh, okay. So syscom isn't the file. Syscom is it is a file in the sense that it is a database file, but then you have to say which record from syscom you want to include. And the one that actually has these common terminal definitions and everything is called keys.h. So let's go back to the program. And we include from the syscom file the keys.h include file. Did I get that right? Yep. So now that is where we'll get the definition for this $cs constant. So that's our clear screen constant. So let's just make sure that works. Let's do basic hello world. Okay, 0 errors. So now if we run hello world, it should do the same thing, but now we're using the constant, so we don't need to remember that -1 is the magic clear screen. Yeah, so not too bad. That's not too exciting. What we can do is, say something like maybe clear the screen. I guess I can keep that. So at $clear screen. And we can go to, say, the first line and maybe, I don't know, 25 in and say planet information. Let's just see what that looks like. Oh, I got it in the wrong order. That should be line number and then, column number and then line number. Okay, planet information. So this is 0-based, it looks like. So the first line is line 0. There we go. So that's about what we're expecting. Now, we have our planet file, of course, list.fl. And when we look at our planet file, of course, we had those multiple attributes, and some of them even had multi-value fields inside of them. So if we want to get data from a file into our program, and of course, if we're writing a program on our multi-value database platform, a lot of the work is going to be accessing files, working with those files. So if we go back to the documentation here, you'll find that there is a file open command. So let's go, yep, here we go, open. So you can open a command, give it the file name, optionally read only if you're only going to read from it in your file, in your program, to a variable. Okay, so we're going to assign this open file to a variable that we'll be able to reference in the other functions. And if there are errors, we can handle them. If it's successful, we can actually embed what we want to do right here for different kinds of errors. So sort of less severe errors than what on error is going to do. You can have other statements that you run. We can look into that with some other commands that we're going to use. But it essentially looks like this, right? So open the file name to the variable name. If it doesn't work, so if this doesn't work, else, we're just going to abort the run with this error message. So let's do that. We can go back to the terminal and we'll edit our hello world program again. And we're going to open planets to, we'll use a variable called planets.f for planets file. And then we will say, else, and I'll just do what they did in the example there, else abort cannot open planets file. Now, you don't have to close files. I think that gets taken care of automatically when the program ends, but for consistency and compatibility with other multi-value systems, you can do a close command just to be explicit about it. Not plants, planets. Made the same mistake here. Now, once the file is open, we can read records from it. So again, if we look in the documentation and go down to the read command, you read into a variable. So we're going to populate a variable called var from the file, comma, the record ID. And it can also have this then else thing. So we would say read, and we'll make up a new variable. We'll just call it planet singular because it'll be the information on one planet. And then what was it? From planets.f, which I still have spelled incorrectly. Planets. So from planets.f, comma, the record ID. So we just used the 1, 2, 3, 4, 5. So Jupiter is 5. And then here's where I can say again, else abort, can't find record. So at this point, planet has the contents of record 5 in the file planets. So let's just print that. If I say print planet, CRT planet, let's run this program. Compiled with no errors, that's good. Run hello world. Okay, interesting. So what we're getting is that raw representation of that data for the key 5 in the planets file. Now, this and this and this, right? These are the field marks. So that's just character 254 in a UTF-8 terminal. The character value 254 is not a valid character, so it's just showing a little missing character symbol here. Unlike the original actual pick system, which translated these to different characters for display, this just shows the raw character string. So we're seeing the field marks as these question marks. Then we're also seeing the value marks, which is character 253, because again, in a UTF-8 encoding, which is what my X term is set to right now, those aren't really a valid character to display. But you get the idea here. This was our whole record, right? We had attribute 1, we had attribute 2. This was the radius with the implied decimal place there. We have attribute 3, which was the probes. Attribute 4 was the probe launch date. Attribute 5 were the moons. And then attribute 6 contained the radiuses of the moons. So that's cool. So that works. So I can open files and I can read records by key. So I can do that indexed lookup of an entry in a file. But of course, this isn't something that we can display to our users. But that string format, the format I get when I read from a file into this planet variable, that is what QMBasic calls a dynamic array. So just like regular basic, we have the dimension statement. And if we look at the docs here, we'll see that. And so this is how you can make a regular array like any other basic implementation has. Here we go, dimension. It can be shortened to the word dim, just like in other basics. And you give it the name of the variable that you're creating. And then it can be multidimensional or two-dimensional at least for the number of array elements. And then you access them just like normal. So if we go back and we say dim myArray 5, I can say things now like myArray 1 equals hello, myArray 2 equals goodbye, so on and so forth. But these are fixed size, and again, they're just like traditional arrays. These dynamic arrays are really these multi-value strings. And because there's a single string that's delimited by the field mark and the value mark, and then actually the sub-value mark, there's a special syntax in QMBasic, and this dates back to the original PicBasic, where instead of using parentheses to index, you can reference parts of the dynamic array indexed inside of angle brackets. So the first attribute of the planet record is the planet name. I can get to that with planet angle bracket 1. So let's display that. Right? So just like that, it's able to pull out the first attribute. Similarly, if I say, I want the second value of attribute 3, we can say attribute 3, but then I can also further index on the values. So in the multi-value field, starting at 1, I can get to all of those values. If I also then used the sub value, which I think is that character 252, you'd be able to get to that by using a third level of indexing. But in this file, we only use fields and then values inside of fields. So I can compile that, run it, and I get Pioneer 11, which is the second value in the third attribute. So that's kind of cool. We can also directly manipulate dynamic arrays this way. So right now, there's only, we have 6? Yeah, we have 6 fields in this planet record. So I can just directly change value. So I can change the name from Jupiter to, I don't know, Zeus. And now let me move my print line for just the whole dynamic array below it. Unassigned variable. That needs to be in quotes. It's a string, not a variable. Okay. Why didn't that work? What did I do? Oh, because I ran it with the CRT command. Right. We want to set planet 1 equal to Zeus. That should work. Okay, so it changed it. So you can change that. And now if I use the write command to write this record back to the database, and in fact, we can do that. Let's look at the documentation for that first. Write will be down with the W's. Right, so same thing, write variable to file record instead of read variable from file record. Now, if you're going to read with the intent to update the record, you can use the read u statement here, which will take an update lock on the record in the file. This is very important to do, of course, because this is a multi-user system. So you don't want to run into a race condition where you read a record, somebody else changes the record, and then you make changes to your old copy and write it back. So the system supports transactions, it supports locking, so you can build robust multi-user applications in these multi-value platforms. And when I write, it automatically releases the read lock. If I end up deciding not to write, I would need to run, I think it's just release. There's a release command here. Yeah, release, and that'll go ahead and read any read update file locks that my code has taken out. And I assume, but don't take my word for it, I assume when you reach the end of the program, it probably releases the locks that you have, like it would automatically close the files, but shouldn't depend on that. You should probably always explicitly release stuff. So I've read it, I changed it. We can write it out to the console here, but then we can say write planet to the planets file 5. You can do the error handling. I won't for the sake of brevity here, compile that program, run it. And now if I sort my planets, sure enough, we no longer have Jupiter, we have Zeus. So the other interesting thing about editing these dynamic arrays is, like we said, we currently only have 6 of the attributes in the file. Let me print a before and after. We can have it create and pad out the file as necessary. So if I say change attribute 15 to Zeus, this will pad out enough blank attributes such that I get to 15. Similarly, if we say 15 subvalue 4 equals hello, let's see what we get here. Compile it, run it. So you can see it did pad out such that I now have an attribute 15. And then these are also value marks. I know we can't really tell the difference on screen here, but these are value marks to then be the 4th value. So 1, 2, 3, 4 in what is now a multi-value field. Of course, these are fields not in our dictionary. So if I sort planets, we're not going to see anything different because we don't have any fields defined to print out or anything for those additional attributes. But the important thing is that we can easily manipulate these records from our files by directly indexing and referencing the attributes and the values here. Now, it's not great programming practices to depend on just constant numbers like this, right? We had to know that the name of the planet goes in attribute 1 in the planets file. So we can create our own header files or include files that will let us use the symbolic names for our attributes. And there's a tool to generate this automatically based on our dictionary. So again, we put all that work into building our dictionary to teach the system about the layout of this file. If we say generate, and then we give it the file we want to generate the header from, which in this case is planets, it will ask us if we want to treat this as a dynamic array or matrix. We're going to do dynamic array, which is what we've been talking about. It will ask for the prefix for our tokens. So if I'm including multiple headers for multiple files, each of which has something called name, we don't want them to clash. So I'm going to say planets, and then it'll do planets.name, planets.radius, and so on and so forth for us to reference them. Now, these preferences were actually saved in the dictionary for this file. So if I generate planets again, it won't ask me for those options again. It'll just remember that. And in fact, if we now list the dictionary for planets, we can see that there's this X type entry called $include, and that includes that prefix that we wanted to use. So it doesn't ask us again. And then the default is dynamic. So the fact that we have an include record, but we haven't, I don't remember where it stores the flag for dynamic. I might just do or matrix. It knows that we want the dynamic array. So anyway, all of that is to say we now have, if we list our BP directory, it has created this planets.h file for us. And if we look at that file, bp planets.h, you can see it generates these equate statements for us. So planets.name is 1, planets.radius is 2. So it tells us the attribute position for our different named attributes. Also, it gives us the conversion code for the attributes that have conversion codes. So if we go back, if we just run our Hello World program again, right, we're getting the number raw, right? We're getting dates, right? What day is date 1524, right? That's the number of days since December 31st, 1967. Off the top of my head, I don't remember that is, what would it be here? That would be March 3rd, 1972. But I don't expect my users to know that either off the top of their heads. So looking back at that header, we know, okay, that's a date conversion, but we also will want to know how to display these numbers correctly. So we have the conversions there. And I think the way that we use those from code is there's either is it just conv? I don't think it's this convert. No, is it, let's see. Program control, logical. I think it's probably just, is it oconv? Oconv, perform output conversion, right? So this will be able to take that conversion specification and prepare it for output. So let's try that. We can edit our Hello World program again. From our own BP, we're going to include planets.h. And let's not do the editing anymore. We don't need the write. We'll just do a regular read. And we can build out here. We can say CRT planet name, and then concatenate that with planet.name. And we can see, we'll say equatorial radius in kilometers, concatenate that with oconv, and then I think we're going to say planet.radius, and then we can give planet.radius.cnv as the converter, or the conversion code, and that should give us that. Now, we don't know how many probes we've sent to Jupiter when we're here in the code. So I think there's a function called dcount that will give us a count of elements in a dynamic array. Let's see if this works. Let's look at the dcount function here. Dcount. String delimiter. So yeah, so we need to tell it if we're looking for field marks or value marks. The field mark character is available as the special @ constant @fm. The value mark is @vm. So if we go back into our code, we can say probes equals dcount of the planet, and I think the field name is probe, so planet.probe. And we want to count how many of them are delimited by the value mark character. So let's just write that out to make sure that worked. We're expecting 2 probes. Let's run our program and see if we're on the right track here. Nope. I don't know where it is in my command history. Basic hello world. Uh-oh. Oh, it's because it's planets, not planet. Was that... oh, yeah, I can see it right here. We used planets as our prefix. So let me... we can just do a planet dot with planet dot with planets dot. Yep, so that's the correct... Okay, compiles with 0 errors. So run hello world. And that's working just like we thought it would. So we're getting the planet name. We're getting the value formatted correctly, the same way we said we wanted it formatted in our reports. And it tells us that there are 2 probes that we have sent to Zeus, Jupiter. Of course, we can modify planets 5 and change that back to Jupiter. Okay, so let's just finish making our little informational screen for planets, and then I think we'll probably call it a day. So obviously we need a way to loop through the entries in these multi-value fields. So as you'd expect, let's go back to the documentation here. We probably have something like a for loop or a while loop. Yep, for next. So we can loop through. So we're going to start at 1, and then we're going to go to however many probes we have, and we're going to run a certain number of statements, and then we go next to increment the counter, go through it, and then when we're all done, we'll fall out of that code. So if we see here, should be pretty simple. You just say for I equals whatever number to whatever number. We'll do our code, and then we'll go to the next I. So let's take a look at that. We can go, let's see. So we have our probes, currently has the count. So we'll just leave that as it is, and we'll say for I equals 1 to probes. We'll indent a little bit here. We'll say probe name, and maybe we'll indent this under the planet a little bit. So I'll put a couple spaces there. So probe name, and give it the planet. We're in planets.probe, and then we'll additionally index by the probe that we're on. And then let's give ourselves a couple spaces. And just so we can go to a new line, I'm going to suppress the carriage return there, and we will we'll say probe, or we'll say launch date. And then here's where we're going to need to use that oconv function again, because we know that the dates are in that internal format. So planets dot launch date indexed by the value I that we're on. And then we'll give it planets.launchDate.cnv. And then we go next I. So let's see if that works. No errors compiling it. And there we go. So we're able to loop through those subvalues in the multi-value field. And for the top level attributes, we can just print them directly. We get the conversion correctly. And because we're using those symbols in the header file, if we change the data definition, if we update all of our records, our program, after we regenerate the header and recompile it, will always be in sync with our actual data, as long as everything that we're using is consistently following the definitions in the dictionary. So again, I can always regenerate the planets header if I were to change the dictionary, and then I can recompile our hello world program, and it would pick up any changes to the header. Obviously, if we're talking about a programming language, there's all sorts of stuff you can do. It does have your standard, we talk about, flow control here, common blocks. Sorry, not common, but do they really talk about at this point? Yeah, right. So you have your if loops. You can have while loops. It is structured programming with block syntax, so it's not like original COBOL where you can't really figure out nested if statements and else statements very easily. You can write good readable code in a structured fashion with good block delineation. Of course, you can make subroutines and functions that you're able to call from your programs. Those can be stored in separate files so that they can be used by lots of programs. The only difference between a subroutine and a function is that and I probably always get this backward, but so subroutines, you call, functions can actually return a value, right? So you can say something equals function, you'll get a value back. Subroutines, you can just use in and out variables. Everything I think is basically called by reference. So the subroutine is able to modify the variable that's passed into it. And that's how you can get more than one value in and out. QMBasic also supports object-oriented programming. You're able to declare classes, and then I assume, yeah, you can inherit stuff. So it looks like you can have public and private variables and subroutines and classes. So if you do want to model things in an object-oriented fashion, QMBasic has you covered. You can do bitwise operations. You're able to do all sorts of stuff, like I said here. So it is a full-featured programming language. Of course, it has everything you'd expect from BASIC, but then it also has a lot of good functionality for working with these dynamic arrays and matrices, which can be multidimensional things. So you can do a set of operations against all of the operations between a two-dimensional array and a one-dimensional array, and it will sort of figure it out. So if you're interested in that, you can play with that. But that's, yeah, that's probably about it. Maybe the one last thing we'll look at is like, oh, well, okay, I know that we looked at Planet 5, but what if I just want my program to print out all of the planets in the planet file? That's probably the last common thing we'd want to look at here. So there is a way to build what's called a select list. So if I say select, I think it's just select planets.f, my open file here, that will build into my default select list number, which is 0. And then I'm able to read items from the select list. So let's go, and in fact, let's go to the documentation here. And we can look at select. There's select. Yeah, so my file variable, I can optionally give it a different list number. So I can keep track of multiple lists that I'm iterating through at a time, but by default, list 0 is used. If you don't get all the way through, at the end of your program, you'll want to clear your select lists. So there's this clear select list or clear all of your select lists. That won't leave select lists sitting around after your program ends. Unlike some other things, this won't automatically clear. Select lists are actually stored in a select list file, so they can be shared. They have meaning at the TCL prompt, so certain commands, if a select list is populated, will run on the select list instead of prompting you for input or asking you what you want to run on. So you just select, and then you can just read through your list. And it will actually read that list into a dynamic array. Or you can have it return the next item from your select list and do it one at a time. So let's look at that. So I select planets. This is going to go into 0 by default. To be safe, we're always going to say, was it clear select? And now we said we can read list. What was the syntax of that again? Read list into a variable. So read list all planets. Now at this point, if I print this out, I'd expect a field mark separated list of the IDs in the planets file. So let's print all planets to the terminal here. We'll compile that. Oh, there's an error. Oh, expected then or else. Do I need... Is that required on one of these? The list, if the then clause is executed, if var contains one or more items, I would think those would be optional. Let's see. Then CRT all planets. See if that fixes it. Okay, I guess because it's common enough that select list might be empty that they do just want to be explicit about it. Let's see if that actually works. Hello world. Yeah, that worked. So the select list is a field mark separated dynamic array. And again, just like if we say list planets, we'll get them in database order, which is effectively random. But if I sort planets, I get them in that key order. So similarly, I can go in and instead of select, there's an S select, which will be a sorted select. So if we compile and run, I now get them in key order, 1, 2, 3, 4, 5. So just like we then looped through the probes, I'd be able to loop through the keys in the database, and I would be able to say, read into planet my variable, or read variable from planet file, comma 1, comma 2, comma 3, but I'd be using the variable that I'm looping over. So that's how you'd be able to write a program. Just like we iterated through all of the probes, we'd be able to iterate through all the planets and then display the planet. So given that there's actually nothing different about the code we already wrote to loop through the probes at this point, I'll leave that as an exercise to the reader instead of taking the time to do that. But that is how you'd go about doing that. So that is going to be it for now. Hopefully that gives you an idea of, once you have the underlying database capability, if the built-in functionality in terms of generating reports and editing data with the modify tool, which probably isn't what you'd normally have end users enter data into your application with, you're able to write these programs in QMBasic and do whatever you want. So be sure to check out that documentation. This is really how you'll learn about how you can do all of these things. You're not restricted to reading just the database files. You can also read sequential files from disk. This is how you might import data from a CSV. There are actually some CSV support functions here, so you'd be able to piece together importing data that way by writing a program that just reads a file from disk. There's a read sequential that goes along, or there's an open sequential, and then that gives you the file that you can read with read sequential. And if we look at CSV here, just since I mentioned it, CSV dequote can quote and dequote, CSV type strings, turn them into field mark separated strings, all that kind of good stuff. And there's a function, I think, to do it in the opposite direction as well. So yeah, lots of capabilities here. All the standard flow control stuff you'd expect. We have the nice terminal addressability stuff to just make it easy for you to build nice layouts on screen. And that's all in here. An area that I haven't gone into is, given that you're often building screens where you want to show a lot of fields and you want the user to be able to interact with them and enter data into them and stuff like that, is there's actually a built-in screen driver, and you can build out screen definitions with this program called SCRB. This is actually somewhat complicated. I've played around with it a little bit. I'm starting to understand how it works and how you're meant to use it. This is one of those cases where there is complete reference documentation on it, but there's no example of how in the world you're actually supposed to use it from a program. So you build out steps, which are really kind of the fields on the screen that you might want to show and let users put data in, or they could just be display fields. They support field validation. They support the input and output conversions. They support positioning them on the screen where you want. It's a really powerful system. But you define all of these, and then at runtime, you're able to run a screen definition using the screen subroutine here. So you give it the screen you want to run, you give it the data that you want to pre-populate anything on that screen with. You can start from a particular step, and then you can get back some status information when it's done to tell you how the user got out of the screen. So cool stuff. And just to give you an example, the screen builder itself is actually built with this screen capability. So if I make, I'm going to make a new file to hold my screens. So that's create file. It doesn't need a dictionary, so data only. And I'm just going to call it my screens. Now, if I use the screen editor and I say my screens, and we'll just call it, I don't know, planet display, we get the screen builder. And the screen builder, we can set a header for our screen. We'll say planet display. And if I go into a step, if I say step 1, this whole screen is built with the screen builder and is being driven by the runtime screen driver. So I can say, okay, let's go to field 1. And, the name of the step is going to be maybe planet name. This isn't displayed on the final screen, but it's so you know what your steps are when you're looking at them. Types can be input or output or basically non-display X. We'll let users, maybe input screen names. If you want to clear the screen when the user gets to the step, you'd say yes here. We'll say no here because we want to keep maybe any other fields on the screen at the same time. Anyway, we can then say, okay, planet name. And if there are other steps that should be displayed on screen at the same time, I don't know what you would use that for. Here's where I can say, okay, I want this to display on row 3 of the screen and maybe column 5. Text mode is if you want reverse video or some other attributes. Field is the attribute in the dynamic array that's passed in that you want to display as the value for this field on the screen. So planet name would be 1. You can also reference the dictionary names. So planets, file planets, the name attribute in the dictionary, it'll figure out that is the value 1. Value subvalue, again, if you want to display a specific then value, if this is a multi-value field. If you want a character at the beginning of the input, you can see in this screen, they're probably using the open bracket as the prompt character and the closed bracket as the end mark, just so you can see where the field is on the screen. We can follow that same convention. Fill character, if you want something other than blanks, if you don't fill up the whole line, we don't really need that. And then data row and data column is, okay, where do you want the actual input field next to the name? So we put name at 3.5. It tells us that's 4 characters long. If we want to do a little bit of quick math to put it after the column ends here. So we'll put that on line 3 so it matches up. The data column goes, 5 plus 4 is 9. Maybe we'll give a little bit more space. We'll say 11. So you get the idea here. How big on the screen should it be? We'll allow it to display 15. Conversion is going to be those conversion codes. So a date should look like a date. Justify, left justified, end marked, close bracket. We can allow more characters than we display. So we can allow, say, 25 characters, and it will actually scroll inside that field. Yes, it's required. And then you can do a number of input validations, including calling subroutines that it'll pass the data to, and you can return if it's valid or not. Can you go backward from this field? What step should I go to next, if not step 2, if we're on step 1? Help text, so if the user hits F1, this is where the name of the planet goes. Error message if the validation fails. Planet name is required. You can control some keyboard actions. If you want to give the user a select list, if they hit F2, you can actually pop up a list of values to select. This could be dynamic by looking for keys in other database files, whether function keys are enabled. If they hit a function key, do you want the screen driver to exit and return that to your program so you can handle it? And I don't even remember what key value is. So that's how you define one field, one step to display on these screens. Of course, you can go to step 2, do the same thing over again. I want to copy what I said for step 1 into step 2. And now I can just change my, this was what, radius. And instead of row 3, let me go back to 6. We'll display this on row 4. And instead of row 3, we'll display this in row 4. Of course, value 9 should be planet's radius. And the conversion, unfortunately, I don't think there's a way to have it reference the dictionary here. I'd have to look. In fact, does it tell me? Entering required output conversion codes. Yeah, so I think I might have to just remember that this was a MR2 comma field. And I suspect to go back in the database in the correct format, you would do that as well. So here you say, equatorial radius of the planet in kilometers. And we can say planet radius is required. So you define all these screens. And when you're done with that, I can go back. I think R is returned to the main screen. If I paint the screen, I think that'll give me a sample of what it might look like. Okay, yeah, so I should have left a little more space there. But you get the idea here that this is what the screen is going to look like. I can simulate running a step. So step 1 was name. And you can see if I enter more text, it scrolls, but now I hit 25, so I can't enter any more text. If I just leave it blank, it'll say this is a required field. And when I'm done with step 2, by default, it goes to the next step. So I hit enter or tab, and it took me to radius. So we'll call that, 54.32. And there is no step 3, so our status ends up being -1. You might define your last step to have, instead of next step, automatically incrementing to step 3 or whatever the next step is. You can put a code there to tell it, okay, we're done. So that's the screen builder. We can, I think, F files that. Yep. So we exit the screen builder. And the way, again, you'd have to use that at runtime. In fact, I mean, I said we're not really going to get into it in this video, but here we are. I've already explained half of it. Let's edit our program again. So first of all, let me remind myself, we called it my screens, and we called it planet display. Okay, so my screens planet display. Let's see if we can do this on the fly here. We'll do a new file. We'll call this our hello screen. Begin hello screen. And we'll typically include our syscom keys.h just so that we can get the screen positioning stuff. I don't know that we'll need it in this scenario. But the first thing you need to do is read the screen definition to pass to the screen runtime. So we can say we need to open the file. So open, we say, what was the syntax? Is it open file name? My screens. Let me give it the variable. I already forgot the syntax. Let's look at open. Right, open file name. This can be read only. Okay, to variable. So open file name, read only to variable. Open file name, read only to screen file. We can have an abort, cannot open my screens. And then we will read. So we need to read into a variable. So we'll just call it scr from screen file. And our key here was the name, planet display. Else abort, cannot find planet display. Misspelled abort there. That should be an R. At this point, we're done with screen file. And now SCR is a dynamic array that has the whole screen definition in the format that Screen Builder builds it in. So the actual screen call, let's go back and look at that again. We call !screen with the screen, with our data, and then the step we want to start on. There's some special steps, or we just run, through starting at whatever step we want. And then a status variable that we will get some status back from. So we will need to create these variables just so that there's something there. So screen data step status. So we can say my data is equal to blank, my status is equal to blank, and we should be able to call screen with the screen, SCR, with the data, and then the step. So let me show you what happens if we start at step 1, which is typically where we would want to start, and then status. And then after running through the screen, let's just go ahead and print out the data we get back. Okay, let's compile that. Hello screen. Expected case or transaction after begin. That's because I said begin, not program. Great. Run hello screen. Okay. So that didn't quite do what we would want, right? Because we just said, remember in the step 1, we said no to clearing the screen first. And we're only seeing the name prompt. We're not seeing anything else here. But if I say Jupiter, now it presents the radius prompt. I can say 432. Okay, the screen driver exited. And sure enough, it gave us back a dynamic array in the correct format that would ultimately go into our planets file. But this wasn't quite the behavior we wanted. So let's edit our program again. And this is why, if I go back to the documentation, you can see we have a special step called 0. This will just clear the screen and then paint the text and data from all of the steps. And that's just one of those X steps that just gets skipped over. So let's try that. Instead of starting at step 1, we go step 0. And we will compile it again and run it. So that's interesting. It's better. We got the header of the screen. We got the form printed out. But now we're just back to the TCL prompt. We're not actually in the form anymore. So step 0 clears the screen, prints the form, but it doesn't then actually let the user interact with anything. So the last step to make this all work is that we would then, after printing the whole screen, we will now run the form starting at step 1, which does not re-clear the screen because we didn't say step 1 clears the screen. And it will actually wait for user input and then run the user through the successive steps. The other thing we can do here is we can start with my data actually having existing data. And then that will get painted when the screen is first painted, and then we can change it as we go through the screen. So let me delete this definition of my data, and we'll just build a dynamic array here where the first element is Jupiter, and the second element is, let me actually get this right this time. This would be 71492, and then remember the implied 2 decimal places. And if we compile and run the screen now, unrecognized variable my data, okay. Maybe I do actually need to have it equal to something before I can start indexing it. Yeah, kind of like arrays have to be declared with dimension first. I think the variable has to exist. Yep, that's better. Okay, so now we're in business. We displayed all of the steps with the current values that are in the data I passed in. I can just hit enter, right? I can edit a value. I can just hit enter to accept whatever was already there. Maybe we decided that it's actually now 5. And now when I'm done, I get the dynamic array back that has the updated values. So that 2 changed to a 5. At this point, I could write that back to my database file, and you would have a nice entry system that you've built up that your user is able to use from your program. So I'll point out in the screen builder documentation, let's see, SCRB, where did it go? Here we go. There is support here for how you would build out repeating steps for your multi-value fields. So if you wanted to have a certain number of steps on the screen that then fill in those multi-value fields, so I could have multiple lines for probes, multiple lines for spacecraft. In that case, right, if you can't fit as many as you need on the screen, you might want to do something other than printing the whole form out. You might have steps that then, do clear the screen and start at the top of the screen for the probe list when you get there and the moon list when you get there. That, of course, is getting into more complicated use of all of this, but there is support for this, repeated steps. And when you look into the things like the columns, where does it talk about? Yeah, data rows. So for repeated rows, it can automatically add an index on top of your base row that you're displaying on the screen. So you can build out those multi-value entry forms using the support that the screen driver has for that sort of thing. So it'd be nice if there was a nice comprehensive demo of kind of the recommended good way to use all of these screen builder features, but I haven't found one yet. The screen builder itself, like I mentioned, is actually built with the screen builder and run with the screen command here. So you can sort of get some ideas. The nice thing about all of this being open source, and then most of these system commands and everything are actually written in QMBasic, is that you are able to look at the source for these things. So I think we go to the GitHub repo. This is the same both in the official upstream ScarletDME repo as well as my fork of it that has a couple of fixes. If you go into QMSys, I think you'll find the screen builder in, let's see, the admin tool is actually defined as screens. They're in a hash file, but the basic program, sorry, let me look for this here. GPL basic. And I think if we just look for screen, yeah, screen. So here is that screen driver subroutine. It's nearly 2,000 lines of basic code, but this is how you would be able to, if you really want to learn, okay, how was that screen builder itself built? Well, here's all the code that it's running. The screen builder can also generate header files. You can reference your steps by name, those kinds of things. So again, you don't have to remember, oh, step 18 is the probe entry step. No, if I want to start the user at probe entry, I'd be able to have an automatically generated header file that I can say start at step, screen.probe entry, something like that. So cool stuff. Probably something that is useful if you are really going to build a full-featured application where you're going to have data input forms for your users. I noticed in the source code for the screen thing here, right? So this was the one from Ladybridge Systems. The screen stuff isn't part of sort of the common baseline of these PIC systems, but I'm guessing most of the products probably have something like it because building screens is really what you're probably doing when you're building these terminal type applications. But I did notice in the code here, let's see if I can find it. There was a reference to Yeah, Universe. So I don't know if this screen driver originally came from Universe, if it was an open source thing that at some point they brought into QMBasic, but I even saw a, maybe it was in the header file or the screen definition. But yeah, I saw like basically an if else block where if we're in OpenQM or if we're in Universe. So the screen builder might be used by a couple of the different multi-value systems. And like I said, for the modern ones that don't have this screen builder, I would think maybe they have their own way to do it, because right, if I was looking at these products, I think having a way for developers to easily build and run screens without having to code all of that logic from scratch would probably be a useful feature. And that's going to be it for today. Thank you so much for watching. I hope you have some ideas now of maybe little programs you can make in QMBasic, run them in ScarletDME. And yeah, lots of good resources online in terms of learning at least the basics of getting started in OpenQM and a little bit of programming for it. Again, if you want to run this pretty easily, at this point, I would recommend just spinning up my Docker container. You can find that on Docker Hub, and it will have instructions right here of how to run the exact same image that I started up to run what we're connected to in here. So it's been fun learning about these pick systems. Like I said in the last video, I was aware of their existence from the legacy of the Dynix library automation system. And actually, at the time that I was using those, I didn't know what pick was. I had no idea what language or environment it was implemented in, but I learned about that later. But a coworker of mine, a friend of mine, actually left the company we were at and went to work for ADP Dealer Services. So we think of ADP, at least in the United States, I don't know where else they operate, as the company that you get your paychecks from, because a lot of companies outsource their payroll to ADP. They also have a whole division that makes software for car dealer service departments. And that was all written in QMBasic. And so I think at the time they were using the Universe implementation, originally from VMark. IBM owned it at the time that he went to work for that company, and now owned by Rocket Software. But anyway, that's where I first kind of learned that this was even a thing, did more research on it. That's where I then learned that that's what that Dynix library system was written in. Anyway, fast forward many, many years now, and it's been fun to finally actually dive into it, learn about it, learn the programming a little bit, learn about the database structure. So I hope this process has been interesting and fun for you as well. As always, let me know down in the comments. I should at least talk slowly enough where I can get the words right. Let me know down in the comments if you are going to go off and build an application in QMBasic here in ScarletDME. Or I should point out that the other products like Universe, Rocket Software does have pretty generous trial license terms for that. So if you just go to their website and fill out their little form so they can put you in their marketing database, you can download Universe for Linux, Unit Data for Linux, and Windows, Universe for Windows, I think. And the license is good for like a year, right? It's a limited, I don't know if it's like a 3-user trial license or something, but certainly enough to play around with. Just if you want to see another, modern commercial implementation, you are able to do that. But in terms of having fun, all of the features in terms of multi-value databases and a full-featured basic language in a multi-value system is all here in the open source ScarletDME fork of that OpenQM product. Because again, OpenQM was at the time and still is a commercial product that's used in production by people. So it's a good, robust system, and it's been a lot of fun to play with. So thanks so much for sticking around. Unless something groundbreaking happens or comes to mind, this will probably be the end of the multi-value video series. But if there are areas that you think might make an interesting video that I should explore, feel free to send in suggestions. Otherwise, yeah, have fun. Thanks for watching. Bye-bye.